Welcome back, geology fans. Last episode we talked about chemical weathering leading to pedogenesis, soil formation, and 2 episodes ago we looked at ion mobility and secondary mineral formation. And this leads to the formation of soil horizons, the layers seen in soil profiles. The soil profile characterizes the changes in soil chemistry and appearance as you go from the surface down to the unweathered bedrock. It is impossible for one location to have all the various horizons identified in soil profiles, but we will look at an idealized soil profile. First, we assume that there is sufficient rainfall for vegetation and water to leach downward, so we start at the top where the rain and soil moisture support plant growth, which leads to plant death, which creates the top O, or organic horizon, with greater than 25 to 30% organic content. This layer was recognized as separate from the layer below it later on, and so the O of the organic layer falls out of the initial soil pattern of A, B, C from top to bottom. So O is now on top, followed by the A horizon below. The A horizon is also known as topsoil, and is the main portion of soil supporting rooted plant growth. Very important to agriculture. Thus, in an area under cultivation, this A horizon and the O horizon above will most likely be highly disturbed, mixed, and overturned. Organic humic matter is present in the topsoil, A horizon, making it black to brown in color, but there is mostly mineral matter present. The next horizon down was also added after the initial ABC designation, and so we get an E horizon when weathering and leaching water is significant. In the O horizon, the O stands for organic, and here in the E horizon, the E stands for eluviation, spelled with an E, which needs to be kept separate from illuviation, spelled with an I. So, spelled with an E for exit, the illuviation means the removal of materials, ions, and clays, whereas illuviation, spelled with an I for introduce, is where the moving ions and clays accumulate. So the E for illuviation horizon is a mineral-rich layer with the mobile ions and clays removed, having been flushed downward by leaching water. With silicate clay, iron, or aluminum having been removed, the E layer is dominated by sand and silt-sized particles of resistant minerals. We get back on the ABC train with the next horizon down, the B horizon. We saw the E horizon illuviating, removing clays, iron, and aluminum, but they build up again in the B horizon, also known as the horizon of illuviation, spelled with an I. There is no original rock structure left in the B horizon, and a heavy accumulation of secondary minerals. There is rock structure still present in the C layer below the B, which is generally defined as highly weathered parent rock, or saprolite, the general term for chemically rotted rock. Going down, you will eventually hit unweathered bedrock, which we can give the letter R as a designation in our soil profile. So from top to bottom, O, A, E, B, C, R. Repeat it to yourself. O, A, E, B, C, R. Again, you will not always find an idealized soil profile like this, and often find one or more horizons missing depending on degree of weathering, geology, and climate, but they do occur in that order downward in all cases. Those are the master horizons, but these can be subdivided using lowercase letters. Some of these are specific to a particular horizon, like the O horizon, which can be OI, slightly decomposed organic matter, OE, moderately decomposed organic matter, or OA, highly decomposed organic matter. Other subdivisions could be applied to more than one master horizon, such as P for plowed, which is usually affecting the O and A horizons. In arid to semi-arid areas, water often does not leach downward but reaches an ultimate depth before it evaporates. In such cases, the highly mobile calcium and magnesium can't keep traveling with the evaporating water and drops out as either desert varnish on the surface of bedrock directly or as a K subdivision horizon, often a BK horizon in the soil dominated by microcrystalline calcite called caliche. In dry areas, the loss of the overlying O and A horizon, you might not have any O horizon in dry climates, will result in exposure of the K horizon, which is known as hardpan.
Okay.
K horizons turn soft soil in the master horizon into amazing concrete, which is a nightmare for drillers. Drilling in caliche can cause the K horizon to fuse into an even harder fused material. It is no use to go through all subdivisions, but if you have strong interest in labeling soil horizons, look up master soil horizons and subdivisions. If you see further subdivisions, you can give it a number in the sequence. So if you have a B horizon with plinthite, it would be a BV horizon. But if you saw two distinct color layers in this section, you could label them BV1 and BV2 and so on. Unless it is a pure organic O horizon, there will be mineral matter in the soil, and the sizes of those mineral particles are another way to categorize soil. We use a trinary diagram to graph out the three main particle sizes, the smallest three, of clay, silt, and sand. Recall that clay is made of particles smaller than 0.002 millimeters. Silt goes from the 0.002 to 0.05 millimeters, and sand is 0.05 millimeters to 2 millimeters. Silt-dominated soil is called silt, sand-dominated is sand, and anything over 60% clay is labeled clay. You don't need much clay to start seeing it increasing water retention, plasticity, moldability, cation exchange capacity, CEC, through a very significant rise in surface area. Loamy soils are preferred for agriculture, and the word loam really means clay, so you need some clay to help with rooted plant growth. A sandy soil would need a constant supply of nutrients through the groundwater or a hydroponic system, but add some clay and nutrients can be stored on large surface areas of those clays and be released again to the roots when needed. But too much clay and water can't get through the soil, which isn't so good for rooted plant growth. So a decent mix of clay, silt, and sand, a loamy textured soil, is best for agriculture. Just search soil texture images to get a copy of this particular diagram if you need it. Great, I've got a soil texture chart, but how do I really use it? How do I measure the relative proportions of clay, silt, and sand? Search soil texture by feel flowchart, and you should get a diagram that looks like this. You take 25 grams of soil. Everybody knows what that means, right? Okay, about a golf ball-sized lump of soil. And assuming it's a little dry, you add water until it becomes plastic and moldable, but isn't leaking extra water out. If you're too wet, add a little dry soil until that plastic limit is hit. If it keeps falling apart and not sticking together in a ball, that's sand. Otherwise, you have a ball of soil which you then work between your thumb and forefinger to make a ribbon of soil of approximately equal width and thickness. If it falls from its own weight immediately as it gets over your finger, that's loamy sand. But if it extends, you see how far it extends. Using centimeters, our increments are 0, 2.5, and 5 as we go from 0 to 2.5 centimeters long, 2.5 to 5, and over 5 centimeters long. And as we get longer and longer ribbons, we are getting more and more clay in the soil. The last step is to determine silt content, which tends to feel more slippery and smooth when wetted just above the plastic limit. Use a smaller amount, get it wet, rub it in your palm with your finger, and depending on how smooth and or gritty it feels, with the grit being sand, we can break down the type of loam textured soil we are dealing with. And carry a lot of water or be near a water source. This is not a test to do if water is at a premium. A related soil property is soil structure, which is how the particles of soil material clump together. This in turn can influence how well water gets through and is retained. Spheroidal structure means the soil particles turn into small rounded to subrounded pellets. This structure is porous and permeable, that is, able to hold and pass water through the soil, and the subrounded crumbs have even higher porosity and permeability. This structure is more likely in the A horizon. Down in the E horizon, you may start to see more platy structure with a drop in porosity and permeability. The fact that there can be soil below our A horizon should not make us complacent about soil erosion and loss. The E horizon has been leached of many nutrients and can have this platy structure, all bad for plant growth. As you get down into the B horizon, where materials are accumulating, you might see blocky texture, either angular blocky or subangular blocky, or prismatic texture, rounded tops or flat angular tops. And with that, we dug into large-scale soil properties and classification. When we come back next time, we will dig a little deeper into soil properties, classification, and nomenclature, here on Earth Explorations.